So we are now wrapping up our unit on rotational motion. We just finished with the notion that we use the analog of F equals ma. You know, if you apply a force, you can get a mass to accelerate, or in other words, to change its momentum. By the same token, if you apply a torque, something will have moment of inertia, you can get it to accelerate in an angular direction. So torque equals I alpha is the analog to F equals ma, and we just finished up talking about that. And we define what moment of inertia are and how the more mass that's located away from the center of the axis of rotation, the higher the moment of inertia, the harder it is to get it to actually rotate or spin. So that's kind of where we left off. Today we're going to talk about rotational kinetic energy and angular momentum, both terms we've heard before, momentum and kinetic energy. So we're going to apply them now to rotational situations. One thing to mention, yes, is that moments of inertia can actually vary or change, not like mass, which typically doesn't change, but you can change the moment of inertia just by some geometric changes, like bringing mass from further away in towards the center. So that will affect the type of problems we see. Okay, so kinetic energy of a rotating body. Well, let's think about kinetic energy of a translational body first of all. So that would be like you have a little ball that's falling through the air, okay? And you want to know what is its energy at any moment of time. Well, it's going to be 1/2 mv squared. So that's what we have for any kinetic energy of a body. But if we have a kinetic energy of a body that's moving and rotating, you have to think about both types of energy, the translational energy and the rotational energy. So you say 1/2 m times the v of the center of mass squared, but then you have another term which is and this is the energy stored in just moving, okay, as it falls or travels along a road or something like that. And then you have the rotational kinetic energy, which is 1/2 I omega squared. And remember, I is the moment of inertia. So notice the analog. I, moment of inertia, to mass over here, omega to speed over here. Okay, so this is a rotational version. So when we're talking about total kinetic energy of a rotating body, we have to include both the translational and the rotational kinetic energy. So if you have a wheel and it's rotating, it would have a moment of inertia of I is mr squared. Remember, you can find moments of inertia from your study guide, so you can look those up. If you have a wheel where all of the mass is located on the outside, it's like a hollow cylinder, it has a moment of inertia mr squared. So in this case, the kinetic energy that's rotational is going to be 1/2 mr squared, which is the moment of inertia, times omega squared. Okay, so that would be the rotational energy. And you just take the total energy, two energies, and add them up. Okay, it is helpful to know that if you have like a wheel, for example, something that's spinning and moving to the right, the center of mass, here's the center of mass right there, the speed of the center of mass is just going to be r omega. Or another way of saying omega is going to be v over r. Okay. So here is a practice problem that I'm going to take you through, and then you're going to get to your own practice problem here in just a second. So if you have a bike wheel, it has a radius 0.6 meters, and it is 0.8 kilograms in mass, and we're going to assume that all of the mass is located on the outside of the wheel. Here's the axis of rotation right here in the middle. That we need to know to get our moment of inertia. And it's rolling at 7.0 meters per second. Now, 7.0 meters per second, that is a linear speed. You can tell because it's meters per second, not radians per second. So you need to know that as you're going to find the different types of energy. So here we go. Translational energy is 1/2 mv squared, v being the center of mass, which is at 7.0 meters per second. So we go 1/2 times 0.8 kilograms times 7 meters per second, quantity squared, for a total of 19.6 joules, or we're going to round it off to 20 joules. We're going to go with two sig figs, my 0.6 and 0.8, just assume that those are 0.60 and 0.80. Okay, so that's the translational. That's the energy you get from having the wheel just move from left to right. But now we have to get the rotational energy as well, which is 1/2 I omega squared. So we have to look up what is I for a hollow cylinder, and we just talked about it. It is mr squared, so 0.8 kilograms times the radius, 0.6 meters squared, or 0.29 kilogram meters squared. That is the moment of inertia for the wheel. But now we have to get the energy, 1/2 I omega squared. So omega, remember, is v over r, so that's going to be 11.7 radians per second. So the total rotational kinetic energy is 1/2 I omega squared, 1/2 I omega squared, which is 19.7 or 20 joules. So just coincidentally, You get 20 joules of rotational, 20 joules of translational for a total energy of 40 joules. Now, are these two numbers always going to be the same? No, they just happen to be. It's just a coincidence they were in this particular case. Okay, moving on. So when we talk about mechanical energy for a rotating object, you think about like conservation mechanical energy. You could use energy and have fun toys like say you have a yo-yo on a string, and you have your yo-yo, and your yo-yo unwraps and it falls down and it creates its own rotational kinetic energy and translational kinetic energy. So it starts with potential, which turns it into translational and rotational. It goes all the way down to the bottom, and then whoop, it goes back up again. So that's a fun little toy that is using this notion of conservation of mechanical energy with a rotating object. Okay, now here's a problem that you get to try. So very similar to the one we just saw a minute ago. You're going to calculate the total kinetic energy of a rolling tire, the rotational plus translational. So pause the video and go ahead and try to work the problem out and see if you get it right and if I get it right, because I guess it could be a mistake in my work. Anyway, so compare our work. So pause the video and then I'm going to reveal the answer. Okay, I'm assuming you're back now, and so here we go. As you try, hopefully translational kinetic energy, 1/2 mv squared, and then omega is v over r again, so 1/2 I omega squared. I is in this case, let's do a different color here. I is in this case 1/2 mr squared, because in this case we have a solid cylinder, which has a different moment of inertia than a hollow cylinder, or a wheel where all the mass is located on the outside. So we get the moment of inertia, and then we go 1/2 I times omega squared to get 204 joules for a grand total of 610 joules. I basically rounded that off to 2 sig figs. It's actually 614, but I rounded off to 610. Okay. All right, so let's talk about momentum. Momentum was a term we defined and understood when we're talking about linear motion, P equals mv, and we talked about the impulse momentum theorem, which says if you apply a force over a period of time, you're going to get a change in momentum. But if there is no force applied over a period of time, there is no change in momentum, which means that the momentum before equals the momentum after. So we have m1v1 equals m2v2. Or if you have lots of different objects, m1v1 plus m2v2 plus m3v3 equals m1v1 prime plus m2v2 prime plus m3v3 prime, etc. So momentum conservation. So let's talk about what happens with rotational motion. The rotational analog. We don't have P, we have L. I do not know why. But the analog for mass, remember, is inertia, and so moment of inertia, I, is going to be our analog for m, and then omega is our analog for velocity. So P equals mv, L equals I omega is angular momentum. Now, if you apply a torque, remember torque equals I alpha, torque equals I alpha, right? Or F equals ma, sort of, I like that idea. If you apply a torque, you're going to get a change in the angular acceleration. But if you apply no torque, then you will not get a change in the angular acceleration. So we say that momentum is conserved. So if there's no net torque, I initial omega initial equals I final omega final. And what's interesting about that is you could be spinning around by having your arms extended holding weights, but then when you pull in the weights, you've changed your moment of inertia. So if your moment of inertia changes, then omega is going to change in response because angular momentum is conserved. So when you see an ice skater, so you have an ice skater here by putting their hands extended, that creates a higher moment of inertia as she's spinning around, but then so she has a large moment of inertia, and she has a small angular velocity. But then when she pulls in her arms, then she has a smaller moment of inertia and a larger angular velocity. Okay, so that's why she goes super, super fast when you pull your arms in. So ballerinas know this concept, and ice skaters for sure. Or funny physics teachers standing on a rotating stool. Again, large moment of inertia over here, and small angular velocity, and then when he tucks his arms in, smaller moment of inertia. Remember, your moment of inertia is small if the mass is close to the axis of rotation, which is right here, and then larger angular velocity. Now there's a special case of angular momentum we want to talk about, which is if you have a point mass that is revolving around a central source. Now it might be something that's held by a string, or it might be a planet that is being held by gravity. So the idea is the angular momentum in this case is just going to be, as it turns out, mRv. That's the angular momentum of an object who is a point mass rotating around its center. And we're going to use that information to talk about Kepler's second law, which we remember said that a line that connects a planet to the sun sweeps out equal areas. So this area, let's get a different color, like purple. This area is going to be equal to this area. And what happens as a result is when the planet is in orbit, and as it comes around, it goes fast through here, and then it goes slow through there. So this area is going to be equal to that area, and it means it goes faster on one side than the other. And Kepler, remember, observed that and became one of his empirical laws, but nobody understood why that was true until we started to understand the notion of angular momentum. So here we go. Let's look at the angular momentum of this particular problem. We're going to argue that as a planet is orbiting around the sun, there is no external torque applied. It is just, once it starts going, it keeps on going and going and going. So angular momentum is conserved. The angular momentum at any location in time, or location here, whether it's here or here or here, is going to always be mRv. So what we can say is that mRv initial equals mRv final, angular momentum. Okay, so let's see what we can conclude from that. Okay, now, area of a sector. Okay, so it turns out the area of a sector is really close to 1/2 times the radius times this arc length s. Okay, kind of looks like a triangle, right? So like 1/2 base times height. So that's the idea of getting an area of a sector. It's really close. It's not exact, but it's close. And s is going to be, you could say, remember, distance equals speed times time, so vt. So s equals vt, so we get this becomes 1/2 rvt. So here is our area formula. Area of our sector is 1/2 times the radius times the speed that's traveling there times the time. Okay, now back to angular momentum. Initial equals final. But in the case of a planet orbiting around the sun, the masses are the same. It's the sun, the mass of the planet, so those can cancel out. And you're just left with RV equals RV. Now if we just take each of those and multiply both sides by 1/2 and recognize, and then multiply by time, like how much, give the same amount of time travel for each of them, so we multiply by 1/2 and a t, then we get the law of areas. Okay, so the area of the first sector is going to be equal to the area of the second sector. Why? Because of the conservation of angular momentum. Remember, the other two laws, the first law and the third law, we understood once we understand the law of universal gravitation, because it was the inverse square law that governed those two laws. Okay, so here is a conservation of angular momentum problem. You have an ice skater with an arm and leg extended, has a moment of inertia of 20 kilogram meters per second. His angular velocity is 8 radians per second. If he spins faster, okay, so he tucks his arms in, whew, he goes faster. What is his new moment of inertia? Okay, so we know I1 omega 1 equals I2 omega 2, and we are given that I1 is 20 kilogram meters per second, and omega 1 is 8 radians per second. We're given that omega 2 is 14.0, and the question is, what is I2? Okay, so conservation of angular momentum. Kind of the key giveaway to an angular momentum problem is when something happens to change the moment of inertia, and they want to know what is the resulting change of the angular velocity. That's how you know you're talking about a momentum problem. So I'm going to say I1 omega 1, which is 20 kilogram times 8 radians per second, is equal to I2 omega 2, I2 times 14 radians per second, and then I just solve for I2, and I get 11.4, which I'm going to round off to 11 kilogram meters squared. Okay, so that's it. Good luck with your work.